So anyway, we need appropriate solutions. Jason's going to be the only one playing. Everybody's, you know what? There's days that no offense, I'm not going to call on you. I'm going to make them use their brain.
We use nitrate, yeah.
Nitrate. So go get a bottle of nitrate. Oh, there is no bottle of nitrate. We're 3/4 of the way there. Nitrate. Sure, why not? So let's put a little copper nitrate here. Ah, good. So we're going to put some copper nitrate here. And over here, maybe some silver nitrate. And we use the nitrate because it's going to be a non-reacting species, right? It's not going to precipitate out. It's not going to cause any other side reactions to occur, okay? And then what do you want to put for the salt in the salt bridge? Sure, why not? I think I used potassium chloride in the one that I just made, but it doesn't matter. And we'll put some NaCl in here. All right. And now to find out if we actually get something, we can put a voltmeter here. Okay? All right. So there we go. So now, with all that being said, how would we find the cell EMF? Go ahead. I'm sorry, what's that? Okay. 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 Okay, to reverse. That's good. And therein lies a question. What's that? That's not the question. What do you guys know about copper?
It could be. Oh, which copper?
Which copper? Because there's two. There's copper 1 and there's copper 2, right? Just for fun, let's use copper 2 because that's the one we're going to run into most often. Okay, so they're written as reduction potentials, right? What's the reduction potential of copper 2? Say this again. And what's the reduction potential of the... Okay. Okay. I'm not even going to get into that. And what about the silver? What is it? Positive? 0.80. Okay, so with that being said, clearly, which one are we going to have to reverse? The copper 2. Do you guys see that? The more negative number. Either way, Sydney, but I also like to throw in the more negative because when we get back to the bottom end. Okay. So, So we reverse this and make it an, I'll just do it down here, rewrite it. Everybody hunky-dory? Okay. Writing the overall reaction, we get silver ion plus copper yielding silver plus copper 2. However, does the electron transfer equalize? Yes, no, or maybe? No. So we're going to have to multiply this process by 2. So it's 2 silver ions forming 2 silver atoms. Okay? And what is the E cell? Positive point. Everyone together now? 4.6 volts. You guys good? All right. Okay, I am going to let you do the next two on your own. I will tell you that the reduction potential for silver chloride in number 4, the reduction potential for silver chloride is plus 0.50 volts. That's not in your list. Haha.
Silver chloride.
voltmeter still out
Should
somewhere?
work, I guess.
Didn't they have that out
So,
yesterday?
oxidation. And the potential is 0.28 because it's got a reduction. See, this is weird. I don't know what to do with the silver chloride.
Cobalt not in there? I'm pretty sure cobalt's in there somewhere.
Cobalt's in the back. It's in the back. Page 8. Well, I mean, we can determine the potential difference that he told us. Yeah. But as for actual reaction, well, I guess it doesn't really matter. You know what the cathode is. I want to know how to do that thing. I don't know.
Nah.
Silver chloride is salt.
Alright.
So why would you want that as a
I should actually make one more solution someday. Nothing to do there.
blue plus blue?
I should not use these beakers.
Or should we use those beakers? What if the glass reacts? Yo, number 4. We got the answers, but I don't know what to do.
Whoa! A little crazy there.
It's been contaminated by the air. Again.
How you doing?
Remember Mr. Yoder's class? Were you in Mr. Yoder's? You were in there with Mr. Yeah. And there was some interesting people.
Okay. Just for fun, I just want to show you the condition of the electrodes.
Copper oxide, is that copper?
And we have a
Auger bridge.
salt bridge, which may or may not work. There's not much, and these are not 1 molar solutions. I have absolutely no idea what their concentrations are. But we're getting some movement there, aren't we?
Yeah. You jostle it around.
There we go. Yeah, we're getting about 0.3 or 4 there, aren't we? Give or take. Yeah. Yeah, at least it works. And again, these aren't 1 molar, so 2 things. 1, they're not 1 molar solutions. I have absolutely no idea what concentration they are, but they're less than 1 molar, so we're not expecting as much of a potential difference. 2, the actual voltmeter itself, especially one like that, analog one, will also absorb some of the potential difference to get it to work. So electronic ones reduce the amount of that. But anyway, the fact that it's actually happening is good.
What metals did you use?
Oh, just copper and zinc. So this is the one that the first one we did, right?
Yeah.
Right. And I can't remember, what was that supposed to be, 1.34 or something like that? 1.1. Okay. Anyway, so I'm going to go to question B first on example number 3. Which electrode is the anode? Cadmium? Okay, good. What did you guys get for your your E cell? 0.26. Yeah, now I have slightly different numbers because when I created these notes, I was using a different textbook in which the standard reduction potentials were given, and then slightly, I had 0.27. Either way, good enough. Okay, 0.27. How many electrons were transferred? Two. There were 2. Okay. Let me see. Example number 4. Which electrode is the cathode in this scenario? Yeah, right. The silver containing side. And what did you guys get for the overall reduction potential? You know what? I told you wrong. Dang it. It's okay. You guys did it right. No, what I did is I gave you the answer.
Oh.
Instead of giving you the cell potential for the silver chloride. My bad on that. You guys want to switch things on this?
Silver chloride.
Okay, the silver chloride cell, I've got to make a note of this. Is positive 0.22. Is it in the book?
Yeah.
And the cobalt was in the book.
Yes.
Really?
Yeah.
Then I'm gonna. My kids lied to me a few years ago.
Oh. That's right. Where is it? It's there. It's there. It's right there.
It is in there.
6 above the standard.
They were lazy, weren't they?
Yes.
Well, at least it's 0.22. So you guys probably looked that up, didn't you?
Yeah.
Yeah, my bad on that. Where's my pen? So I essentially gave you the answer. Okay, so any problems with this? Pretty straightforward? It's not hard, it's just different. Something you hadn't seen before. Has this gotten any better yet? No. Yeah.
For number 3, how are we just, like, will we just use tin 2 or, like...
I use tin 2. It would have to be specified. Either they're not going to use one of those, so you don't have to worry about it, or it would be specified. Did you use tin 4? It makes your life easier if you use tin 2. Many of you probably went that route. Do they have more than one cobalt in there, just out of curiosity? They have cobalt 3 also? And again, to make your life, it doesn't really matter on that one. Did most of you go with cobalt 2? Yeah. Okay. Yes. Well, they do now. It used to be, up until they redid the exam here a few years ago now, one of the components that you got, not only did you get the periodic table, the equation sheet, but you also got a standard reduction potential sheet. Okay? Now the information is provided, embedded in the problem somehow or other, or a means to figure it out by other ways. So somehow, you don't, to answer your question and your concern, you do not have to memorize these, which is the only thing you really cared about. Okay. Yeah.
Number 4, with the silver chloride, what would be the appropriate solution? Because the reaction
Is a solid.
Yeah.
Right, and so you're going to have to construct something there.
Okay. I mean, we didn't really need it. But
No, I get that. I know. You'd have a big chunk of silver chloride. I don't know. Because remember, silver chloride is insoluble.
Right.
So theoretically, you could just put that in a little thing of water and you'd be good to go. Theoretically. Anyway. Moving on. Do I want to do this? Yes, I'm going to. This used to be a thing. This next part, oxidizing and reducing agents. Okay? The AP is no longer focusing on the agent piece. They're no longer having you identify agents. And again, this is one of those things that in your lifetime, if you guys continue on into another chemistry class, you will be exposed to this, so I'm just going to put it in the back of your brain. Okay? So, agents are the species that cause the other thing to happen. So, for example, let's look up at example number 2, since we're on the same page here. Okay? Which is the species that oxidized? The copper oxidized. What caused the copper to oxidize? What was present that caused, and I think I have it up here, what was present that caused the copper to oxidize? No, the nitrates had nothing. The nitrates were spectator ions throughout the whole thing. Oh, there's more questions I had to answer up here. we'll do it now. What was present that caused the copper to oxidize? Okay, is the copper just going to oxidize just sitting there on its own? No, something caused it to oxidize. The silver. If the silver had not been present, would the copper have oxidized? No. So the silver caused it to oxidize. So therefore, the silver was the oxidizing agent. It caused the copper to oxidize. On the flip side of that, though, what did the silver do? It reduced. Did it reduce on its own? No. What caused it to reduce? What was present that caused it to reduce? The copper. So the copper is the reducing agent. So the agents are the other side of what happened. So copper oxidized. It was oxidized by the silver. Silver reduced. It was reduced by the copper. Does that make any sense? Remember, we've always said that you can't have one without the other. Well, one thing does one thing, the other species is what causes that to happen. It's called an agent. Okay? So, the more positive the reduction potential. I already talked about this with a couple of you in conversation during the little study hall piece, okay? When looking at that table, and we already looked at fluorine as being the most easily reduced. Yesterday we talked about why that's true, which brought us to the whole thing that, yeah. So the more positive the reduction potential, the more easily reduced it is. Therefore, it's a stronger oxidizing agent. It's more easy. Think about it this way. It's a fight for the electrons. Fluorine's going to win. Okay? In fact, it's going to beat everybody. Now, that means it's a really strong oxidizing agent. It's a thing that's going to cause everything else to oxidize. Are you following there? Okay. These are typically species that have high positive oxidation states. Now, through all our redox stuff that we did back in Chapter 4, can you guys think of any species that have high positive oxidation states? Any elements that have high positive oxidation states? There should be some that are on your brain. What's that? No. What species? Permanganate ion. The manganese in permanganate ion was a +7. There's a lot of reducing that can be done there. Would you agree? The manganese has a long way to go to reduce, doesn't it? From +7 to 0? That's a long way to go. Therefore, it's a very good reducing agent. Or sorry about that, strong oxidizing agent. Causes other things to oxidize really, really well because it's taking electrons from them. Can you think of another species? Sulfate's not bad, although it has you're going to find out later that it stays together pretty well. Yeah? Boom. We've used dichromate ion quite a bit, right? Remember the chromium was +6? And there's one more that you guys have had some experience with. You may not think of it. So far we got permanganate ion, dichromate ion, the chromium and the dichromate ion, and the nitrogen in nitrate ion. What's the oxidation state of nitrogen in a nitrate ion? +5. Okay, those are all typically pretty good oxidizing agents. Also, can you think of anything else really, really common that might be an oxidizing agent? Say it. Oxygen. That's actually where the whole concept, the whole phrase came from, is oxygen. What does iron do? Oxidizes, rusts. What does zinc do? I mean, we already see it a little bit. Magnesium. You know, we had to, I think in some of the labs we did, we had to use the steel wool to clean off the metal because it had oxidized, right, by oxygen just existing in the presence of oxygen. And the halogens in general, okay? The halogens in general, clearly fluorine is the one with the greatest, but also the other halogens. So we've got permanganate ion, the manganese and permanganate ion, we've got chromium and dichromate, nitrogen and nitrate ion, oxygen, clearly, and some of the halogens. Okay, on the flip side, reducing agent. I guess I never really identified, I guess I did. The more negative the reduction potential, the more easily it is oxidized. So as you go down that list, you run into species that are more easily oxidized, which means gives up the electrons pretty easily. That means they're very good reducing agents. What are some examples? Hydrogen gas, and just looking at the table, just out of curiosity, I want to look at the table. As you work, yeah, absolutely. As you work your way towards the bottom of the table, in general, where are you finding those elements? In what groups are you finding those elements? And which are known as the alkali and the alkaline earth metals, right? Yeah, so there you go. So the alkali and the alkaline earth metals, groups 1A and 2A, and hydrogen are typically stronger reducing agents. They give up electrons really easily to allow other things to be reduced. How much time do I have left? That answers that question. This was almost perfect.